So today we'll be looking at partial fractions and partial fraction resolution. So we know that we can add two or more rational fractions into a single rational fraction. So for example, we have this equation over here. Now what you'll simply do is to turn these two rational fractions into one rational fraction, you'll have to take the LCM on both fractions. So basically this entire fraction will be multiplied by x plus 2, and this entire fraction will be multiplied with x plus x minus 1, and then you'll join them and basically add them up, and you'll get this single fraction. And similarly over here you have three rational fractions, and you can multiply this entire equation with x plus 1 and x minus 2. So you can get this basically in the common denominator of all three fractions. You need this term in the denominators of all three fractions. So you'll multiply accordingly, and basically you know all this from before. So what we'll do now is we'll do the opposite. We need to express a single rational fraction as a sum of two or more rational fractions, and those are called partial fractions. So you'll be given one single fraction, and then you'll basically turn it into a sum of two or more rational fractions. And those rational fractions that are being added up to make the single rational fraction are called partial fractions. And basically expressing one rational fraction as a sum of partial fractions is called partial fraction resolution. So the process of actually converting a single rational fraction into its components that are being added up is called partial fraction resolution. Now, we'll discuss the definition of a conditional equation, an identity, and a rational fraction. So, first, let's discuss what a conditional equation is. Basically, in an equation where two algebraic expressions are equal for particular values of the variable. Now that may sound confusing, but let's just clear this up with an example. You have this linear equation, and once you solve this, you can find out that x is equal to 3 by 2, obviously, because to get x on the left hand side, you'll basically divide this 3 by this 2, and so the value of x is equal to 3 by 2. So 2x minus 3 is a conditional equation, and it is true only if the value of x is equal to 3 by 2. So if the value of x is equal to 3 by 2, the left hand side is equal to the right hand side, and that is the condition. So we have the second example. This is a quadratic equation. So obviously a quadratic equation will have two solutions, two values for the variable. So x will have two values over here, and once you solve this, you'll find out that the values for x become 2 and 3, minus 3, sorry. And basically this quadratic equation is a conditional equation, and it is true only for these two values of x. Now let's discuss what an identity is. It is an equation which holds good for all values of the variable. So basically you have this equation, and this equation is an identity, and its two sides are equal for all values of x. So if you basically plug in any value of x, the left hand side will be equal to the right hand side. So this is an identity. Similarly, you have over here this equation. Once you multiply this bracket and this bracket, the components basically that are inside the brackets, once you multiply them, you get this quadratic equation. So basically the left hand side and the right hand side will be true for all values of x. They will be equal for all values of x. So this is also an identity. Now let's see a rational fraction. Now we know that for example, this p by q, where P and Q are integers. This Z represents an integer. So P and Q must be integers, and Q must not be equal to 0, obviously, because that becomes an undefined result. So this P and Q, for where P and Q are all integers and Q is not equal to 0, it is called a rational number. It is called a rational number. Similarly, if you have two polynomials, P of x and Q of x, and so they are being divided. So P of x divided by Q of x, and Q of x must not be equal to 0, obviously. And it has no common factors. P of x and Q of x have no common factors. So basically, this is the what do you say? The simplified form. This will be called a rational fraction, not a rational number. This will be called a rational fraction because we're dealing with polynomials on the numerator and denominator. So let's discuss proper and improper rational fractions. So basically, you have this rational fraction P of x over Q of x. It will be a proper rational fraction if the degree of the polynomial P of x in the numerator is less than the degree of the polynomial Q of x in the denominator, which that really means is that the highest degree of the variable x in P of x must be less than the highest degree of the variable x in Q of x. So for example, you have these three rational fractions. The highest degree of x in the numerator here is 0, and the highest degree of variable x in the denominator over here is 1. So as you can see, 0 is less than 1, so this is a proper rational fraction. Over here, the highest degree of x is this 1, and in the numerator, and the highest degree of x in the denominator is this 2. So 1 is less than 2. So this is also a proper fraction. And similarly in this one, the degree of x, highest degree of x in the numerator is 2, and the highest degree of x in the denominator is 3. So 2 is less than 3. So this is also a proper fraction. So in an improper fraction, if the degree of the polynomial P of x in the numerator is equal to or greater than the degree of the polynomial Q of x in the denominator. So, for example, you have these three rational fractions. The degree of x, the highest degree of x is 1 over here in the numerator, and the highest degree of x in the denominator is also 1. So they are equal. 1 is equal to 1. So this is an improper fraction. Over in the second example, now it may seem like the highest degree over here is 1 in the numerator and also 1 in the denominator, but don't be fooled. This linear expression in the bracket is being multiplied with this linear expression in the bracket. So once these two brackets are multiplied, the highest degree of x becomes x squared. This is a quadratic equation, and similarly in the denominator we also have a quadratic equation. So the highest degree of x in the numerator and the denominator is 2. So 2 is equal to 2. So this is an improper fraction. Over here in the third example, the highest degree of x in the numerator is 3, and the highest degree of x in the denominator is 2. 3 is greater than 2, so this is also an improper fraction. So let's discuss the first type of partial fraction. So we have been given this fraction, and we need to resolve it into its partial fractions. This is the first type, and basically what you'll do is, so you remember that we have this algebraic identity, x squared minus y squared is equal to x plus y into x minus y. We'll apply the same logic over here in the denominator, x squared minus 1 or x squared minus 1 square, obviously, because any power of 1 will obviously give you 1 as a result. So x squared minus 1 becomes x plus 1, x minus 1. Now what you'll do is, you'll write this particular result in this form: a over x plus 1 plus b over x minus 1. Now, obviously, to turn these partial fractions into one single fraction, you'll have to take the LCM of both partial fractions. So this entire fraction will be multiplied with x minus 1 over x minus 1, and this entire fraction will be multiplied with x plus 1 over x plus 1. So that'll give you this fraction as a result. Now the denominators are same, so we need to make the numerators equal to each other. So 1 is equal to a into x minus 1 plus b into x plus 1. Now what you'll do is, you need to basically eliminate one of the two variables, a and b. So let's just eliminate this a first. So how will you do that? Now look at this. Over here, the a is being multiplied with x minus 1. So you need to make this expression equal to 0. So how will you do that? Well, you'll put x minus 1 is equal to 0, and that will give you x is equal to 1. So you need to put in x is equal to 1. So when you do that, this a will be multiplied with 0 and b will be multiplied with x plus 1. So 1 plus 1. So b is equal to b into 2. 2b is equal to 1, and hence b is equal to 1 by 2. Now you need to eliminate the b term in the next part so that you can find the value of a. How you'll do that? Well, as you know, b is being multiplied with x plus 1. So you'll do x plus 1 is equal to 0. So x will be equal to minus 1. And when you do that, b will be multiplied with this 0, minus 1 plus 1 equal to 0. And a will be multiplied with minus 1 plus minus 1 minus 1. So minus 2a is equal to 1, and a is equal to minus 1 by 2. So we have found the values for a and b. Once you put them in the equation, you'll get this. Obviously, this 2 and this 2, they will be multiplied with the respective denominators. And so you'll get this, and these are the required partial fractions. Now we'll convert an improper fraction to its partial fractions. We'll resolve it. Now you have this fraction. How do you know it's an improper fraction? Well, the highest degree in the numerator will obviously be x to the power 4, because this x square will be multiplied with this x square to give you x to the power 4. The highest degree or the highest power of x in the denominator will be 2, because this linear term is being multiplied with this linear term, and that will give you a quadratic equation which has the highest power of x as 2. So 4 is greater than 2, so the highest degree in the numerator is greater than the highest degree in the denominator, so it is an improper fraction. And how will you basically turn it into its partial fractions? Well, you'll perform division. So you'll first multiply this x square with this term, and you'll multiply the two linear terms in the denominators to get x to the power 4 plus x square in the numerator and x square minus 1 in the denominator. Now you need to divide x to the power 4 plus x square with x square minus 1. So how will you do that? Well, first you need to eliminate this x to the power 4 term. So you'll multiply x square minus 1 with x square. That will give you x to the power 4 minus x square. And you'll subtract x to the power 4 plus x square from x to the power 4 minus x square. And when you do that, the x to the power 4 and the x to the power 4 terms will be cut out, because obviously it's being subtracted. And since this entire term is being subtracted, this minus of the x square will become plus x square. So plus x square will give you 2x square. Now, and obviously this becomes 0. Now, you need to eliminate this 2x square term. So what will you do with this divisor? Well, you'll multiply it with 2. So x square minus 1 plus into plus 2 will become 2x square minus 2. So 2x square will be subtracted from 2x square. That will give you 0. And this minus 2 will be subtracted from 0. So it will give you plus 2. Now, this is the remainder, this is the quotient, and this is the divisor. So how will you express this in an equation form? Well, you see this term, this will be equal to the quotient, so x square plus 2 plus the remainder over the divisor. So 2 is the remainder and x square minus 1 is the divisor. So we get this equation. Now we need to resolve this proper fraction. Why is it a proper fraction? Because because the degree in the numerator is 0 and the degree in the denominator is 2. So now you'll basically resolve this part of the equation by the type 1 resolution that we did before. So you'll turn this x square minus 1 into x plus 1 into x minus 1, and then you'll write it down as a over x plus 1 plus b over x minus 1, the partial fractions. And obviously, you'll take the LCM of these two partial fractions. So a will be multiplied with this x minus 1 and b will be multiplied with this x plus 1. So you get this entire equation. The denominators are equal, so we need to make the numerators equal now. So 2 is equal to a into x minus 1 plus b into x plus 1. Now, obviously, as we've done before, we need to eliminate either of the a and b terms first. So let's say we'll eliminate this a term first. To do that, you need to put x is equal to 1. So a will be multiplied with 1 minus 1, so which is equal to 0, and hence the a term will be eliminated, it will become 0. And obviously the b term will be multiplied with 1 plus 1, so 2b is equal to 2. And now b is equal to 1. You got the value for b. Now we need to eliminate b from the equation so that we can find the value of a. So we'll put the value of x is equal to minus 1 in the equation, and hence b will be multiplied with minus 1 plus 1, so b will be multiplied with basically 0, and hence the b term will be eliminated. The a term will be multiplied with minus 1 minus 1. So minus 2a is equal to 2, and hence a is equal to minus 1. So you found the values of a and b. You'll put the values of a and b in the equation, so you'll get these partial fractions. And now equation 1, which was the result of the division that we had done, will become x square plus 2 minus 1 over x plus 1 plus 1 over x minus 1. So the question that we had, the partial fractions will become this. These are the required partial fractions. Now, let's convert a proper fraction into its partial fractions. So, well, we have this fraction. And how is it a proper fraction? Well, the degree of x in the numerator is 1. And the degree of x in the denominator is 3, because linear term being multiplied with a linear term and that being multiplied with another linear term, well, that gives you a cubic equation, and the highest power of x in a cubic equation is 3. So 1 is less than 3, so this is a proper fraction. However, in this particular example, you can see that we have constants as letters. So this will become a little bit more confusing, but bear with me. Well, as you know, we discussed the first type of partial fraction resolution, and we'll apply that over here. We'll resolve this one fraction into a sum of three partial fractions, and in each partial fraction, we'll have one of these three terms. So x minus a in the first one, x minus b in the second one, and x minus c in the third one. And they will have a, b, and c as the numerators. Now, we'll take the LCM of these three partial fractions. So basically a will be multiplied with x minus b and x minus c, b will be multiplied with x minus a and x minus c, and c will be multiplied with x minus a and x minus b. So we'll get this big fraction. Now, the denominators are equal, so the numerators are also equal. The denominators will be cancelled out and we'll just be left with the numerators. Now, we need to eliminate basically 2 of a, b, and c to get the value for one, what would we say, variable, I guess. So we need to find the value of a, we need to eliminate b and c. To find the value of b, we need to eliminate a and c. And to find the value of c, we need to eliminate a and b. So first, let's put x is equal to a in this equation 2. When you put x is equal to a, all the terms with x minus a will be eliminated. So this entire term will be eliminated because this becomes 0 when you put x is equal to a minus a is equal to 0. And this entire term will also be eliminated because this becomes 0. So we're just left with a into a minus b into a minus c. Now, we get basically now let's resolve an equation into partial fractions using substitution. Now, in some cases, you'll have some difficulty and you'll actually be confused how to convert a single fraction into a partial fraction. And this is one of those examples. So, how will you proceed with this? Well, like in most mathematical concepts, you'll use substitution. So, obviously, when you're dealing with so many square terms like x squared, b squared, a squared, c squared, d squared, it'll become a bit difficult to actually proceed. So, what you'll do is you'll substitute x squared with y, a quadratic term with a linear term. And you'll also neglect the square of each term that we have in this equation. So x squared becomes y, a squared becomes a. You'll neglect the square. The b squared becomes b, the c squared becomes c, and the d squared becomes d. Now, here's what you'll do. This entire expression with so many square terms turns into this simpler expression. The x squared will be replaced with y everywhere, and the other terms will have the squares removed. Now, after that, you'll just proceed it like you'll proceed with any other first type of partial fraction resolution. So this will become three partial fractions being added up, and in each of the denominators, you'll have each of these three terms. So a over y plus b over y plus c over y plus d. Obviously, the ones in the numerator are uppercase letters and the ones in the denominator are lowercase letters. Now we need to find the values of a, uppercase b, and uppercase c. So you'll take the LCM of these three partial fractions. So a will be multiplied with y plus c and y plus d, b will be multiplied with y plus b and y plus d, and c will be multiplied with y plus b and y plus c. So you'll get this big expression, and the denominators are both same, so they'll be cancelled out, and you'll just be left with the numerators equal to each other as such. Now you need to eliminate two terms, two of the uppercase letters to get the value of one uppercase letter. So for example, if you need the value of this uppercase a, you need to eliminate this entire term and this entire term. Basically, you need to eliminate this uppercase b and this uppercase c. So when you put lowercase y is equal to minus lowercase b in this equation, this term will be eliminated and this term will be eliminated. Why? Because this y plus b term becomes 0 as y is equal to minus b. So minus b plus b becomes 0. And so this entire term becomes 0 because everything will be multiplied with each other. Same is the case with this uppercase c. Y plus b is equal to 0. So here's what you'll do. You'll just be left with this entire term that has the uppercase a in it, and this y plus a becomes minus b plus a because y is equal to minus b. Now, you get the value of uppercase a as this. Uppercase a is equal to lowercase a minus lowercase b over lowercase c minus lowercase b into lowercase d minus lowercase b. And now you need to find the values of uppercase b and uppercase c. So when you put y is equal to negative lowercase c in the same equation too, well, that eliminates the a term and the c term. So you'll just be left with this uppercase b term, this entire term. And then you'll just find the value of uppercase b like this. And when you put y is equal to negative lowercase d, the uppercase a and the uppercase b terms are eliminated, and you'll be left with this uppercase c term. And so you'll find the value of uppercase c. And then now that you have the values of uppercase a, uppercase b, and uppercase c, you'll put that into equation 1. What was equation 1? This was equation 1, the initial partial fraction equation. Now that we have the values of uppercase a, uppercase b, and uppercase c, we'll substitute them into this equation. Whoops. And when you do that, you'll get these partial fractions. Now this is a bit messy, but obviously the denominator terms in the numerator fractions will be multiplied with these denominator terms. And so once that is done, you'll get these partial fractions. And this is the partial fractions as a resolution of the equation given in the question, which was this. But you're missing one thing. You remember that these terms were square terms. So you'll now replace all of these linear terms with square terms. So a, everywhere where you have an a, it will be replaced with an a square. Everywhere where you have a b, that will be replaced with a b square. The c's will be replaced with the c square. The d's will be replaced with the d square, and the y will be replaced with x square. So this is the final result of the partial fraction resolution. Now let's discuss how to resolve the second type of partial fraction. So you have this single fraction and we have to resolve it into its partial fractions. Now, we haven't dealt with this denominator before. So how do we proceed with this? Well, the partial fractions for such a fraction will basically have denominators that are in increasing power of the original denominator. So for example, this is x minus 1 whole cube. So the first partial fraction will be a over x minus 1 to the power 1. The second partial fraction will be b over x minus 1 to the power 2. And the third fraction will be c over x minus 1 whole to the power 3. And since that is the limit, this is where we'll stop. Now we have three partial fractions. Obviously, you'll have to take the LCM so that the denominators of the left-hand side and right-hand side can be equal. So obviously this a here, we must have this x minus 1 whole cube underneath every single partial fraction over here. So this a will be multiplied with x minus 1 whole square, so that this denominator will also be multiplied with x minus 1 whole square, and so that can give you x minus 1 whole cube. So a will be multiplied with x minus 1 whole square, b will be multiplied with x minus 1, and c will remain as it is since it has x minus 1 whole cube underneath as in its denominator. So now we have the left hand side equal to the right hand side, and now since both of the denominators are equal, they'll be cancelled out, and so we are just left with the numerators equal to each other. And so this is what you get. And obviously when you actually expand this x minus 1 whole square, you get this x plus 1 minus 2x, x squared plus 1 minus 2x, and b will be multiplied with x and minus 1, so bx minus b. And so in the end you get this equation. But really, this is the best way to solve this equation. Now, for argument's sake, let's just write down the first equation over here, which was 2x squared minus 3x plus 4. So 2x squared minus 3x plus 4. And what was that equal to? It was equal to a into x minus 1 whole square plus b into x minus 1 plus c. So a into x minus 1 whole square plus b into x minus 1 plus c. Now, when we put x is equal to 1 in equation 2, well, this entire part and this entire part will become 0 because this bracket will become 0. So when you replace x with 1 in this equation, you get c is equal to 3. So you have a value for c now. Now we have to find the values of a and b. Now, here's the best part. Remember, when you expand this part, you get basically, instead of just going through it ourselves, you get this. And so, well, we'll write this down over here. So we have a into x squared minus 2x plus 1 plus bx minus b plus c, and that will be equal to ax squared minus 2 whoops 2ax plus a plus bx minus b plus c, and then that will basically tell you that a is the coefficient of x squared and minus 2a plus b are the coefficients of x, and then you have obviously plus a minus b plus c. So here's what you'll do. As you know that the coefficient of x squared on the right hand side is 2, and the coefficient of x squared on the the coefficient of x squared on the left hand side is 2, and the coefficient of x squared on the right hand side is a. So a is equal to 2, obviously. So that is how you get the value of a. Now, how will you get the value of x? Well, the coefficient of x on the right hand side is minus 2a plus b, and the coefficient of x on the left hand side is minus 3. So minus 2a plus b is equal to minus 3, obviously. And then you'll plug in the value of a you found here. So minus 2 into the value of a, which is 2, plus b is equal to 3. And when you resolve this, you find out that the value of b is 1. So now you have the values of c, the value of a, and the value of b. So when you plug that in to your original partial fractions, you get this equation. And hence, the fraction given in the question has been resolved. So let's resolve a rational fraction into a partial fraction using the second type of partial fraction resolution. Over here, things are a bit different than the last time we touched this topic. Over here, you actually have this part, this denominator, and that will actually be resolved by the second type of partial fraction resolution. But it also being multiplied with this linear expression. So how will you deal with this? Well, it's somewhat similar to what we did before. Well, you'll first have to resolve the x plus 2 whole square part of the denominator. And how will you do that? Well, as you remember, you'll have two partial fractions over here, obviously in increasing powers of x plus 2. So we'll have a over x plus 2 to the power 1 plus b over x plus 2 to the power 2. And obviously that is the limit. That is the highest, that is the highest power of x plus 2. So that is where you'll stop with this part of the denominator, and then you'll have to also put in another partial fraction for this x minus 1. So you'll have this c over x minus 1 for this, and now you have to resolve it. So obviously, as with every other partial fraction resolution we've done before, you'll take the LCM of these three. So a will be multiplied with, basically you need this in the denominator, this x plus 2 whole square into x minus 1. So we already have this x plus 2 expression over here. It needs to be multiplied with another x plus 2 and obviously x minus 1. So a will be multiplied with x plus 2 and x minus 1. B has x plus 2 whole square, so it just needs to be multiplied with x minus 1. So b will be multiplied with x minus 1. And c is missing this, the denominator of c is missing this x plus 2 whole square. So c will be multiplied with x plus 2 whole square. And then obviously the denominator is also be multiplied with the same numbers, the same expressions. And so you'll have the denominators equal to each other. Now they can be cancelled. And basically you now have the numerators equal to each other. And so you'll get this expression. And obviously after multiplying x plus 2 and x minus 1, you get this expression, this quadratic expression. B will multiply with bx minus 1, so you'll get bx minus b. And c will be multiplied with x plus 2 whole square, and that is basically the expansion of x plus 2 whole square, and after multiplying everything, you get this big equation. Now, when you put x is equal to minus 2 in equation 2, what was equation 2? This was equation 2. So when you put x is equal to basically 1, sorry, x is equal to minus 2 in this equation, every variable of these three variables, a, b, and c, the ones that are being multiplied with x plus 2 will be eliminated, because when you plug in 2 into the expression, this plus 2 will be multiplied with minus 2, and that will give you 0. So this entire expression will be 0, and c will also become 0 because this part will become 0. So you'll just be left with b into minus 2 minus 1, so b into minus 3. So let's see what happens. See, a will be multiplied with 0 and c will be multiplied with 0. b will be multiplied with minus 3. So we'll have minus 3b is equal to 9, and so the value of b is equal to minus 3. Now, when you put x is equal to 1 in the same equation 2 we did before, basically the a variable will be eliminated and b will also be eliminated. And we'll just be left with c, and that is equal to x plus 2 whole square. And so, since the value of x is 1, 1 plus 2 whole square, so that becomes 3 square. And so 9c is equal to 9, and so c is equal to 1. We have found the values of b and c. Now let's just find the value of a. So we need equation 3. So what was equation 3? Well, this was equation 3. And basically, we'll just have to see what happens. Well, look over here. As you know, that the component of x squared in equation 3 is a plus c. Let me show you again. Look over here. A and c, a plus c. These are the coefficients of x squared. But you notice that on the left-hand side, you have no expression for x squared. You have no coefficient for x squared. So that is why the coefficient of x squared will be equal to 0. So a plus c is equal to 0. And so when you plug in the value of a, and what did you find the value of a? Oh, sorry. When you plug in the value of c, you found the value of c to be 1. So when you plug in the value of c, you find that a plus 1 is equal to 0. And so a is equal to minus 1. Now we found the values of a, b, and c, and when you plug in those values in the original partial fraction that we found, you get this. And so you have resolved the equation given in the question into its partial fractions. Now let's discuss the third type of partial fraction resolution. Well, the first type that we discussed, it had denominators with linear terms, like this term here. All of the terms in the denominator were like this, single linear terms. Now, in the second one, so let's just, for example, let's just write that down over here. So the first type, there was an expression, and basically we're concerned with the denominator. The denominator had basically x plus 2 and like x plus 3 and something like this. So in the second type, the denominator had basically something like this, x plus 2 to the power 3. And so this is the third type. In the third type, the variable has the power. As you can see, there is no variable over here that has a power in it. So this over here, we have a variable with a power. So how do we deal with this? Well, when you resolve it into its partial fractions in the initial step, you have basically this, you get this. Well, you have ax plus b over this entire expression that has the variable with the power. And then obviously you have this linear factor as well, the linear expression, and so you'll have to add that into the other partial fraction. Now, obviously, as with every other type of partial fraction resolution we've done, you'll take the LCM. So basically you need to get this denominator on the right hand side as well. So the ax plus b expression will be multiplied with x plus 3, and so will its denominator. So x plus b will be multiplied with x plus 3, and c will be multiplied with x squared plus 1, and so will its denominator. And so the denominators are now equal to each other. They will be cancelled out, and so the numerators are now equated to each other. So you have this. Now, obviously, when you multiply these two expressions, this is what you'll get. And c will be multiplied with x squared plus 1, so you'll get cx squared plus c. Now, what will you do? Well, you have to, when you put in x is equal to 3 into equation 2, look at this. What was equation 2 actually? It was ax plus b into x plus 3. So ax plus b into x plus 3, and we'll basically add c into x squared plus 1. If I am not mistaken, let's just see. Yep, that's exactly what it is. So this is equation 2. When you plug in x minus 3 into this equation, this part becomes 0. And since this becomes 0, this also becomes 0 since it is being multiplied with it. So the left hand side, when you plug in x minus 3 on the left hand side, you'll get, whoops, let's just see what the left hand side is, 9x minus 7. So 9x minus 7 becomes 9 into minus 3 minus 7. And since this part becomes 0, it is now written down as 0. And c will be multiplied with x squared minus 1. So c will be multiplied with minus 3 whole square plus 1. And so after doing the calculations, the value of c you get is minus 17 over 5. Now, we have to equate coefficients on the left hand side and the right hand side. So equating coefficients of x squared and x in equation 3. Let's see what equation 3 is. Look at this. The coefficients of x squared are a and plus c. So a plus c are the coefficients of x squared. Basically, when you write down this whole expression, you get a plus c into x squared, and what is this? Yes, plus 3a plus b into x plus 3b plus c. So the coefficient of x squared is a plus c. So a plus c is equal to 0. Why is it equal to 0? Because as you can see, the left hand side, which is basically 9x minus 7, it has no x squared term in it. So the x squared term is equal to 0. So a plus c is equal to 0. We found the value of c before. When you plug that in, you get the value of a as 17 over 5. Now we have the values of c and we have the values of a. Now let's equate the left hand side, the coefficients of x on the left hand side to the coefficient of x on the right hand side. So as you remember, let's see equation 3. In equation 3 you found this. This is the coefficient of x on the right hand side, and the coefficient of x on the left hand side is equal to 9. So basically 3a plus b is equal to 9. Now you do that, 3a plus b is equal to 9. As you know, we have already found the value of a, 17 over 5. So after doing the calculations, you find out that the value of b is equal to minus 6 over 5. And so you found a, b, and c. When you plug that into the original partial fraction equation that we made, you get this. And obviously, after putting down the 5 in the denominator and this 5 in the denominator as well, you get this. And these are the required partial fractions. So let's convert this fraction into its partial fractions. Let's resolve it into its partial fractions. So simply, you'll just look at one thing over here. What type of partial fraction resolution are we talking about? Well, the variable x over here has a power, the power of 2. So you'll automatically assume that this is the third type of partial fraction resolution. So if you remember, this is how you resolved a single fraction in the third type of partial fraction resolution. You had one partial fraction, that had ax plus b in the numerator, and in the denominator it had the expression which had the variable x with the power. So the x squared plus 2x plus 5 will have a numerator of ax plus b. And then we have to deal with this second linear expression, and obviously the second partial fraction will have c over the linear expression. Now, you have to make the denominator of the left hand side and the right hand side equal to each other. So you'll take the LCM on the right hand side. So ax plus b will be multiplied with x minus 1, c will be multiplied with x squared plus 2x plus 5. And so now you have the denominators equal to each other. You'll cancel out the denominators, and then you'll equate the numerators to each other. And that's where you get this equation number 2. Now, after expanding in calculation, this is the final equation, which is equation number 3. Now, when you put x is equal to 1 in equation number 2, what happens? Well, this is equation number 2. And when you put x is equal to 1 in this expression, this part, this linear expression becomes 0. 1 minus 1, 0. And since this becomes 0, this ax plus b will be multiplied with 0, and it will also become 0. And now, when you plug in x is equal to 1 over here, and over here, and over here, you basically get this. So now, after doing all the calculations, you can see that the value of c is equal to 2. Now, we'll equate the coefficients of x squared and x on the left hand side and the right hand side. So we'll use equation number 3. So how will we go about this? Well, as you remember, look over here. The coefficients of x squared are a and c, and the coefficients of x are a, minus a, b, and plus 2c. So basically, when you simplify this expression on the right hand side, you'll get a plus c into x squared plus minus a plus b plus 2c into x and minus b plus 5c. So you can see that the coefficient of x squared on the right hand side is a plus c, and the coefficient of x on the right hand side is minus a plus b plus 2c. So a plus c on the right hand side is equal to 1 on the left hand side. Since the coefficient of x squared on the left hand side is 1, a plus c is equal to 1. Now, since a plus c is equal to 1 and we already found the value of c, when you plug in the value of c as 2, you get the value of a, which is equal to minus 1. Now let's find the value of x. As you remember, the coefficient of x on the right hand side is minus a plus b plus 2c. And on the left hand side, we did not have an expression for x. Look over here. Oops. Yes. As you can see, there is no expression for x on the left hand side. So the coefficient of x on the left hand side is 0. So minus a plus b plus 2c is equal to 0. We already found the values of a and c. So when you plug in those values, you'll get the value of b as equal to minus 5. Now we found the values of c, b, and a. When you plug in those values, you get these partial fractions. And so you've resolved the original fraction given in the question into its partial fractions. Now let's do some partial fraction resolution using identities. So we have this fraction and we have to resolve it into its partial fractions. Now you can see that the variable in the denominator has a power. So x has a power of 3. So we'll use the type 3 resolution method. Now over here you'll actually have to factorize this cubic expression into its quadratic and linear expressions. Now you can do that by referring to the lectures in chapter 4 where I've explained how to do this. And once you've done that, you'll basically do what you've done before. Now the linear factor will have one partial fraction, which is this, and the quadratic factor will have one partial fraction, which is this. And so now you'll just do what you've done before. You'll take the LCM so that the denominators on the left hand side and the right hand side are equal. So a will be multiplied with this quadratic factor and bx plus c will be multiplied with this linear factor, and so will the denominators. So now you have this expression. The denominators is now equal, so they will be cancelled out, and so you'll equate the numerators equal to each other. And after doing the calculations, you get this equation, which is equation number 3. Now when you plug in x is equal to -1 in equation number 2, what happens? Well, as you can see, this is equation number 2. When you plug in x is equal to -1, this linear expression becomes 0, 1 minus 1. And since this 0 will be multiplied with bx plus c, this also becomes 0. So this entire expression over here becomes 0. And so you're left with this and this. And when you plug in x is equal to 1 into every x over here, this is what you'll get. This equation. And so 3a is equal to 2 and a is equal to 2 by 3. So we have found the value of a. Now we'll equate the coefficients of x squared and x on the left hand side and the right hand side in equation number 3. What was equation number 3? This was equation number 3. Now when you actually simplify this, you can see that a plus b is the coefficient of x squared and minus a plus b plus c is the coefficient of x, and in the end you're left with plus a and plus c as the final constants. Now on the left hand side, the coefficient of x squared is 1 and there is no expression for x, so the coefficient of x is 0 and you have this 1. So a plus b is equal to 1, since a plus b is the coefficient of x squared on the right hand side and 1 is the coefficient of x squared on the left hand side. So when you equate a plus b is equal to 1, and since you've already found the value of a over here and you plug that in, you find out that the value of b is equal to 1 by 3. Now to find the value of x, as you remember, in equation number 3, the coefficient of x is minus a plus b plus c. And on the left hand side, you see that there is no expression for x. So the coefficient of x on the left hand side is 0. Now we found the values of a and b. So when you plug those in, you find out that the value of c is equal to 1 by 3. And when you plug a, b and c into equation number 1, you find out that this is what you get. Now when you bring this 3 to the denominator, and these 3's will also go into the denominator, so this is the final result. These are the required partial fractions. So the fourth type of partial fraction resolution is somewhat a combination of the second type and the third type. Over here, you have an entire expression inside a square bracket. So that is where the second type of partial fraction resolution comes in. But also you can see that the expression inside has the variable with a power. So That is where the third type of partial fraction resolution comes in. So, how will we deal with this? Well, as you know, we'll have the two partial fractions, one with this term being of the power of 1 and the second one having this expression with the power of 2. As you know, in the second type of partial fraction resolution, this is what you did. You basically had an entire expression inside a certain power bracket. Over here, that's a square bracket. So you'll have expressions in, you'll have partial fractions with denominators in increasing powers of this same expression. So for example, if this was x squared plus x plus 1 whole to the power 3, you would have basically three partial fractions with ax plus b in the first one, cx plus d in the second one, and say ex plus f in the third one. And in the denominators, you would basically have x squared plus x plus 1 in increasing powers up to 3. So now, how will you go about this? Well, as you know, in every kind of partial fraction resolution, you'll basically take the LCM so that the denominators on the left-hand side and the right-hand side will be equal. So ax plus b will be multiplied with x squared plus x plus 1. So that the denominator will also be multiplied with x squared plus x plus 1, and that will end up giving you this. And cx plus d already has x squared plus x plus 1 whole to the power 2, so it will remain as it is. So now the denominators on the left hand side and the right hand side are equal. They will be cancelled out and you'll equate the numerators to each other. Now, what will you do? After actually calculating these entire expression, after multiplying this expression with this expression, you basically get this whole equation, and we'll call this equation number 2. Now, you'll simply equate the coefficients of x cubed, x squared, and x on the left hand side and the right hand side equal to each other. So, look at this. You basically have only one x cubed expression on the right hand side. There is no other x cubed expression on the right hand side. And there's only one expression of x cubed on the left hand side as well. And the coefficient of x cubed over here is 1. So a is equal to 1. That's as simple as that. Now, the coefficient of x squared on the right hand side is a plus b. So a plus b is equal to, well, there is no x squared expression on the left hand side. So that means that the coefficient of x squared on the left hand side is 0. So a plus b is equal to 0. Now, since we have the value of a already from this part here, we'll plug that in to this part, and so b will be equal to minus 1. Now, the coefficient of x on the left hand side is 2, and the coefficient of x on the right hand side is a plus b plus c. So a plus b plus c is equal to 2. Now we have the values of a and b above, and we'll plug those in to get the value of c, which is equal to 2. And the constant on the left hand side is 2. The constant on the right hand side is, well, b plus d. So b plus d is equal to 2. And we already have the value of b from before. When we plug that in, you can see that the value of d is equal to 3. So we now have values of a, b, c, and d. So we'll plug those values in to our original partial fraction that we developed, and you'll basically get this. And these are the required partial fractions.